The first law I'm going to mention is Boyle's law, which says that pressure is inversely proportional to volume under a constant temperature. This means that if pressure increases, volume will decrease. So for example, if the pressure doubles, the volume will be halved. Alright, so now that we've done the fun experiment to see what Boyle's law is, let's go over a problem so we know how to solve this. So in this example, we have a small oxygen canister contains 110 milliliters of oxygen gas. One way to quickly identify what variable or what piece of information a question is giving you is to look at the units. So since that's a unit of volume, then we know that volume will initially be, so I'm going to write V1, is 110 milliliters. So I'm going to convert that to liters, so 0.11 liters. Okay, so it starts off at 110 milliliters of oxygen gas at a pressure of 3 atmospheres. So it starts off with a pressure of 3 atmospheres. Now, although we don't really need to convert it for this problem, it's good to get into the habit. And let me show you how you do it anyways. We're going to convert this to kilopascals. So to do that, we are going to multiply by the ratio of 101.3 kilopascals for every 1 atmosphere. When I write it this way, we see atmospheres cancel because we have 1 on the numerator and 1 denominator, and we are left with our pressure in terms of kilopascals is 303.9 kPa. Alright, so let's continue reading the question. This oxygen is released into a balloon with a final pressure of 2 atmospheres. So P2 is 2 atmospheres. And if we do the same thing, multiply by 101.3 kPa per atmosphere, we get 202.6 kPa. What is the final volume of the balloon? So we're looking for V2. So this is where Boyle's law can now come into play, where P1V1 equals P2V2. So if we sub in what we know, we have 303.9 kilopascals times that initial volume of 0.11 liters is going to equal 202.6 kilopascals times by whatever V2 is. So we just need to divide both sides by P2 in order to isolate for V2. So divide both sides by 202.6 kPa, so they cancel here. And we will get V2 as 0.165 liters, or if you like, 165 milliliters. Let's go to the next gas law. The next law I'm going to talk about is Charles' law, which says that volume is directly proportional to temperature under a constant pressure. What this means is that as temperature increases, volume increases as well. So for example, if temperature were to double, volume would double. Alright, now let's do a question with Charles's law. So in this one we have an open, empty, so there's no liquid in it, 2-liter plastic pop container, which has an actual inside volume of 2.05 liters. So essentially we have a pop bottle. It's the best I could do. And inside you have air molecules in it, filled all the way, right, to have an initial volume of 2.05 liters. Now it's removed from a refrigerator, so it's initially at 5 degrees Celsius and allowed to warm to 21 degrees Celsius. So eventually the temperature is going to become 21 degrees Celsius. What volume of air measured at 21 degrees Celsius will leave the container? So as it warms, the air is going to expand and some air is going to be released. So let's try to figure out what that new volume is. So Charles's law looks like V1 over T1 equals V2 over T2. Now, something important that we have to do here is we need to convert degrees Celsius to the absolute Kelvin scale. To do that, we're simply going to add 273. So our final temperature is then equal to 294 Kelvin. The initial temperature, T1, if we add 273 to that, we get 278 Kelvin. So now we can sub these into our equation. So V1 is 2.05 liters at a temperature of 278 Kelvin. That's going to equal V2, which we do not know, divided by a temperature of 294 Kelvin. So what we're going to do is isolate for V2. So we're going to multiply both sides by 294 Kelvin so that they cancel here. And the other side as well, 294 Kelvin. So now we can put that into our calculator and we will get V2 to be 2.17 liters. Now here's where the tricky part in this question comes from, because it wants to know what volume of air will leave the container. There's still going to be 2.05 liters of air in the container. It doesn't become a vacuum, but it pushes out any excess air. So what we're going to do to figure that out is take the new volume and see how much more that is from 2.05. So we're going to do 2.17 liters minus 2.05 liters. And we get a volume, let's call it expelled volume, to be 0.12 liters. The last law I'm going to mention is Gay-Lussac's law, which says that temperature is directly proportional to pressure under constant volume. All right, the next problem is a Gay-Lussac problem. So let's go through it. A closed empty tank containing air, well, I guess it's not completely empty, it's got air, at 97 kilopascals and 22 degrees Celsius survives intact in a fire. So there's our initial pressure, so P1, and here's our initial temperature, T1. If the tank is able to withstand a maximum internal pressure of 350 kPa, okay, so there's P2, what is the maximum temperature? So we're looking for T2. Okay. And we are going to have to change T1 into the Kelvin scale. So let's add 273 to that. So that becomes 295 Kelvin. Now let's write down Gay-Lussac's law. So P1 over T1 equals P2 over T2. P1 we know 97 kPa over T1, which is 295 Kelvin. P2 is 350 kPa over T2. So we're going to have to rearrange this. We can do some cross multiplying. We can switch these terms, and then this term we can bring up over here. You don't have to switch them both. We can just move our 295 Kelvin up here, like we're multiplying both sides by 295. When we do that, we're going to get T2 is equal to 350 kPa times 295 Kelvin, all divided by 97 kilopascals. And that is going to be 1064 Kelvin. But what we typically like to do, if the question is giving information in Celsius, we should probably return the answer in Celsius as well. So let's subtract 273 to turn this back into the Celsius scale. So when we do that, we get 791 degrees Celsius. Whew. And these three laws can come together to give us our combined gas law formula. Alright, so here's an example with the combined gas law. You can actually do this two ways. I've seen students do the ideal gas law to solve this problem, but if you're using the ideal gas law, you're going to have to apply it twice. Let me show you. Let's read the question. A balloon has a volume of 5 liters, so here's V1, at 20 degrees and a pressure of 100 kPa. What is its volume? So it wants to know V2 at T2, 35 degrees Celsius, and a pressure of 90 kPa. Now you could apply these three to your ideal gas law and solve for the amount of moles in the gas. And then once knowing the moles, you're going to have to then apply the ideal gas law again for a second time to figure out the volume. There's nothing wrong with that, but we can make our lives a little easier on this question by just using the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. And this works because the amount of gas is staying constant, so the number of moles you have isn't changing. Now, we are going to have to first change our temperatures, as always, into Kelvin. So 20 degrees is add 273, you get 293 Kelvin. And 35 degrees, you get 308 Kelvin. All right, so we can sub everything in now. So we have pressure 1, we have 100 kPa times our volume, 5 liters, all over that temperature, 293 Kelvin. It's going to be equal to our new pressure, 90 kPa, times V2, which is what we're looking for, divided by the new temperature of 308 Kelvin. So we can take 308 Kelvin, multiply both sides, so it'll come up here, and divide both sides by 90 Kelvin, so it'll be down there. So when we solve for that, we get V2 equal to, I'll write it all out, so you get 100 kPa times 5 liters times by 308 Kelvin, all divided by 293 Kelvin and 90 kPa. So when you write it all out, you can also look at your units to make sure you didn't make a mistake, and you'll see you're left with units of liters, which is volume. So we get V2 to be 5.8 liters. I hope this tutorial helped.